طيب okay, شباب, السلام عليكم. Inshallah, today we will be talking about the case of unsteady flow. Last time we end up with the steady flow devices. We have developed the equation for a steady flow, general steady flow, either for single stream or multiple stream. And we have applied actually this first law equation in addition actually to the mass equation to some steady flow devices, including turbine, compressor, nozzle, diffuser, and so on. We have applied actually this to many steady flow devices. And most of the engineering system are actually steady flow devices. But actually, what if we have unsteady flow? In this case, we'll see today, inshallah, how we can develop the energy equation and also the mass equation with unsteady flow. Unsteady flow, like this example here, we have unsteady flow either when we are charging a tank, just filling a tank, or the other case actually when we have a kind of a tank that is actually discharging, or there is a kind of leak actually inside this tank. In both cases actually, shabab, we have either flow in and we don't have flow out. So in this case, mass in does not equal to actually the mass flow rate in does not equal to the mass flow rate out. So the case is unsteady flow. Or the second case, we have actually mass out, either we have leakage or we are discharging a tank. So in this case, we have mass out, but we don't have mass in this case. So mass flow rate in does not equal to mass flow rate out. So the case is unsteady flow. Or we can have actually mass in and we have also mass out, like we are filling a tank or something, but actually there is a leak in this tank. So in this case, we have mass flow rate in and we have mass flow rate out, but mass flow rate in does not equal to mass flow rate out, which is the condition for a steady flow. So in this case, we have also unsteady flow. So unsteady flow is either charging or discharging. Charging, which means actually we are filling a tank, mass flow rate in and we don't have mass flow rate out. Discharging is the reverse. We have mass out, we don't have mass in. Or we may have actually mass out and mass in, but mass in does not equal to mass out, and this is the case actually of unsteady flow. Before we study the unsteady flow, we have an assumption here, either we have flow in or flow out. We assume actually uniform property distribution either at the inlet in case of the charging or at the outlet in case of discharge. We assume actually uniform velocity distribution as an example, then we consider actually the average value of the velocity. We don't consider actually any change with time at the inlet or at the outlet, okay? So that we can calculate the properties without just getting into many calculations. So we assume uniform flow at inlet and at the outlet, and we consider the average values of the properties, and those properties are not function of time. But let's consider we have unsteady flow. So let's say we have a flow inside the tube or something, and this flow actually is used to fill up a tank or charging a tank or something. So we have here, let's say we have a flow or stream, and here we have a valve that controls the flow actually to inside of this tank to fill this tank. Let's say we have a steam or something. So in some application, like petroleum engineering, actually we just get the oil from the field and then actually we transport it to fill actually or charge it, actually charging it in big tanks. And then actually we can take from this tank later on to fill the barrel and then actually for exporting. But first of all, we take it from the field and put it actually in big headers, something like this. So in this process, actually we have petrol is coming and then actually it fills this tank. So this process of filling is unsteady process in this case. But let's consider a general example. We have flow and we are actually filling this tank. So in this case, we have mass flow rate inlet. So the condition here at the inlet section, we have mass flow rate inlet with a given pressure, given temperature. This flow actually is coming into this tank. Let's say actually initially this tank has a mass. Let's say this mass is M1. And we are filling actually, this is on a steady process until actually the mass is reaching actually a final mass. Let's say the final mass is M2. And let's say actually while this filling process, we may have some heat is rejected, some heat is added. In some cases, actually, we may get actually fill a tank with some mixture of gases, and we want actually those gases to be in homogeneous state. So in this case, actually, we may have a paddle wheel or something just to mix the gases. In this case, if we have paddle wheel, that means actually we have shaft input power in this case. And in some cases, in cold weather also, we may have actually a kind of electric heating coil just to heat up actually the fluid inside this tank. So the case is generalized. We cannot say in any problem what actually of those parameters will be there. So depending on the state, actually we can study any system under unsteady flow conditions. So let's consider this is actually generalized case, and let's consider actually this is our control volume, and look at actually the surface of this control volume for masses and the energy transfer. And let's apply first of all the mass equation. So if you apply the mass equation for any system, we have mass in minus mass out. That should equal to the change of mass within this system. Okay, mass in minus mass out equal to the change of mass within the control volume. So it will equal to mass in minus mass out. Let's say this is m exit, so m inlet minus m exit. The change of mass, which is the final mass, minus the initial mass, which we call this actually as M2 and M1. So M2 is the final mass, M1 is the initial mass, Mi is the inlet mass, Me actually is the exit mass from this system. So for unsteady flow, mass flow rate N, not mass flow rate, the total mass, this is actually the mass calculated in kilogram, not the mass flow rate. So mass in minus mass out should equal to the final mass within the system minus the initial mass. So this is the final, this is the initial. If he said we have this tank, let's say initially evacuated, so the initial mass, that means the initial mass is equal to 0. So in case if this tank actually is initially evacuated, that means actually the initial mass M1 is equal to 0. But in case if we are filling a tank or charging a tank, so we have mass in but we don't have mass out. So in case of discharging a tank, we have mass out but we don't have mass in. So in this case actually M exit will equal to 0 in case we are charging a tank. Charging, that means we have mass in but we don't have mass out. But if we are discharging, that means we have mass out but we don't have mass in. So in case of discharging a tank, this mass inlet will equal to 0, but we should have mass outlet in this case. Okay? So this is regarding the mass equation. Let's apply also the energy equation and see how we can apply this energy equation in case of unsteady flow. Usually unsteady flow will be considering the total form of the equation. So for the energy, we'll consider the total form in kilojoule, not the rate one. The rate one we have considered in steady flow devices to just get rid of actually the right-hand side term of the energy equation. But here I will be considering the total form of the equation, not the rate form, like the case of closed system. So let's apply the energy equation of the first law of thermodynamics. The first law of thermodynamics will say energy in minus energy out equal to the change of energy of the system, okay, which is the final energy minus the initial energy. And we said this term, the change of energy of the system, if you recall the case of closed system, that should equal to the change of internal energy, the change in kinetic energy, and also the change in potential energy. And this term, change in kinetic and change in potential, is equal to 0 in case when we have actually a stationary system. The system is not moving, which is the case actually of unsteady flow system. So those terms most probably in all application will be 0. That means the change of energy of the system will equal to delta U. So this term, the change of energy of the system will equal to delta U, which is U2, the final internal energy, total final internal energy minus total initial internal energy. But actually the final mass, M2, is not the same as M1, okay? So we cannot say here mass as common multiplied by specific internal energy U2 minus U1, no. It is equal to the specific mass M2 multiplied by the specific internal energy U2 minus M1 multiplied by specific internal energy U1. We cannot take the mass as common because the initial mass is not as actually the same as the final mass, because the case is unsteady flow in this case. So U2, the change of energy of the system, will equal to delta U, which is M2 U2 minus M1 U1. This U is the specific internal energy in kilojoule per kilogram, and this is the total the total energy change within the system in kilojoules. But what about those terms, energy in and energy out? So as we said, in this case, we have mass transfer. The system is not closed. So that means we have the three forms. Energy can transfer by heat, can transfer by work, and the energy also can transfer due to mass transfer. And let's write down this equation. We said delta U, there is a change of energy, will equal to delta U, which is M2U2 minus M1U1. This is the term right-hand side of the equation. But what about energy in minus energy out? So energy in, this term energy in minus energy out, we can just replace it directly. It will be Q minus work, minus because the sign of the work is opposite to the heat transfer, plus energy due to mass in, minus energy due to mass out. That should equal to the change of energy of the system, which we said equal to M2U2 minus M1U1. About this term, we can have here add the summation sign if we have more than one inlet or more than one outlet. This summation sign can be added in this case. But let's write down this equation. It will be Q minus work. Let's take this term of mass transfer to the other side. It will be mass out, which is equal to, we said, M exit. The energy due to mass leaving the system will equal to the mass of the system leaving, the mass of the fluid leaving multiplied by H exit plus V exit squared divided by 2 plus GZ exit minus the inlet mass multiplied by H inlet plus V inlet squared divided by 2 plus GZ inlet. We just took those terms to the other side, okay? But don't forget in the other side, the change of energy of the system, we have this term. Please don't forget actually this term, M2U2 minus M1U1. And this is actually the form of the energy equation in case where we have unsteady flow. So this is a common error that you just say Q minus work equal to M exit multiplied by this term minus M inlet multiplied by this term, and you just forget about this term. This term is very important, okay? Please don't forget, okay? Type this term, as we used to say, this heat transfer, it may be equal to 0 in case of adiabatic, isolated, insulated, or if it is not given or required, it will be 0 also. And it can have also either positive sign or negative sign. Positive if it is added, and negative if it is rejected. And the reverse is the work. Work can be 0 if not given or required. We can just assign it a value of 0. And this work also can be positive if it is produced, and it can be negative if it is consumed. And I think we talk about this actually more than one in our earlier classes. M exit multiplied by this term. Usually this term, all of this term first of all, will be 0 if we are charging a tank. So if a tank is charging, that means we have mass in, but we don't have mass out. M exit is 0. So the whole term will be 0 in case we are charging a tank. And this term, the other term, M inlet, multiplied by this term, the energy transfer by mass due to mass transfer to the system, M inlet multiplied by this term, that term should equal to 0 in case if we are actually discharging a tank. So in this case, the whole term will equal to 0. Inshallah, we'll see once we are trying to solve the problem, you will see actually this equation will be much reduced in this case. Okay. But what about this term? Kinetic energy plus potential energy. Usually they are 0 if they are not given or required. So usually for unsteady flow, those two terms will be neglected. Kinetic energy plus the potential energy, they will be neglected if they are not given or required. Okay, so we'll see inshallah once we start to solve the problem that this elongated equation will be much reduced in this case. Okay, and we can add the summation sign if we have more than one outlet of the system, and we can add actually the summation sign here if we have more than one inlet in this case. Okay, let's solve example and see how we can apply those equations. Okay. This is what we said, and the equations that we have developed. Here in this case, I said we have a rigid insulated tank. Rigid, that means the volume of the tank. Just to try to translate directly, volume of the tank is constant as it is rigid. Insulated tank, that means actually the heat transfer is equal to 0. Initially evacuated, that means actually mass M1 is equal to 0. So the initial mass is equal to 0. And there is actually a supply line that carries the steam. So in this case, the working fluid is steam. So as the working fluid is steam, I will be using the steam table in this case. Okay. So let's look at this problem. So we have a supply line of steam is just going. So this flow, which is steam in this case, is going, and we are filling actually a tank with this steam, and here is a valve. Okay. He said this tank was initially evacuated, so the initial mass M1 is equal to 0. So we have a charging or filling process in this case. He said the flow condition of this steam, the flow condition which will be coming into the system, that means actually those are the inlet condition. So the pressure steam at the inlet is equal to 1 megapascal, and temperature at the inlet section is equal to 300 degrees. Okay. He said we open the valve, so steam is just getting into the system, inside this tank, until actually the pressure inside the tank rises, approaches a value of 1 megapascal. So it was initially evacuated, and then the pressure will be raised actually when we close after opening this valve, the flow of steam will be coming in, and the pressure inside this tank, which was initially evacuated, will be raised actually until a final pressure. So the final pressure B2 inside this tank will equal to 1 megapascal in this case. Okay. At this point, when the pressure approaches this value, he said we have just closed this valve, and we need to calculate actually the final temperature of steam inside this tank. Just look at the naming, Shabab. Initial, we call it 1. So initial mass, we call it M1. Initially evacuated, that means M1 is equal to 0. We need the final temperature, that means we need T2. Okay? Right, he said the pressure inside the tank has been raised until it approaches final pressure equal to 1 megapascal. So this is B2. Okay? But what about here? He said the steam is flowing under such a condition. So when the flow of steam just to try to get inside the tank, it will be getting into the tank under this condition. So these conditions are the inlet condition. Because we have I indicates the inlet, E indicates the outlet or exit, 1 indicate initial, 2 indicate final. Okay, so let's solve this problem. So first of all, let's apply the mass equation. So we can say mass inlet minus mass exit will equal to M2 minus M1. He said it was initially evacuated, this means M1 is equal to 0. And we are filling this tank, so we have mass inlet, but we don't have mass outlet. So in this case, the mass equation will say the mass inlet will equal to the final mass in this case. So M inlet will equal to M2 in this case. So let's apply the energy equation. This is the energy equation, Q minus R K equal to M exit multiplied by H plus V squared plus GZ minus M inlet multiplied by the same term plus M2 U2 minus M1 U1. If you look here, so here we have mass inlet, so we don't have actually mass outlet. So all of this term will be 0. Okay. Here he did not give actually the value of kinetic and potential energy, so this term also as well will equal to 0 in this case. Okay. M1 U1 initially evacuated, M1 is equal to 0, so that term will equal to 0 as well. In this case, he said the system is adiabatic, so we don't have heat transfer. But in this case, we have just a filling, just a flow. We don't have a paddle wheel or electric heating coil. We don't have anything, any kind of this work. So the work is equal to 0. So that equation will be reduced to what? Minus summation of M dot inlet, H inlet, plus M2 U2, that should equal to 0. Or we can say M2 U2 will equal to M inlet multiplied by HN. But we have M inlet is the same as M2. So M inlet from the mass equation is the same as M2. That means the energy equation will give us that actually the final internal energy is equal to the inlet enthalpy in this case. Okay? So let's look here and see we have the final pressure. So we need another property to calculate the final temperature. Okay? So at the case 1, at the inlet, we have P inlet is equal to 1 megapascal, and we have T inlet is equal to 300 degrees C. Pressure and temperature, you can, with this pressure, go to table A5, get the saturation temperature. You will find that this temperature is greater than the saturation, so the case is superheated. I will be using table A6. Then we can calculate the enthalpy at the inlet section. You can get this value, enthalpy at the inlet section will equal to 301 point something kilojoule per kilogram. Okay, so this is the enthalpy H inlet. H inlet is the same as U2. So at the final state, we have V2 is equal to 1 megapascal, and we have the internal energy U2 is equal to H inlet, which is equal to 3051 kilojoule per kilogram. Now we have the final pressure. We have the final internal energy, which is a specific property, which is equal to the enthalpy H inlet. So we have the pressure, we have the internal energy. Go with this pressure to table A5, get U fluid and U gas, compare it with this internal energy, this value. You will find actually that this internal energy is greater than U gas, so the state is superheated. So I will be using table A6 with this pressure and with this internal energy value. Then we can calculate actually the final temperature. You can check this value to equal to 456.1 degrees C in this case. Okay. So this is a simple example for the case of unsteady flow. As you have seen, we have just reduced actually all of the terms of the equation. System is adiabatic. This term is 0. We don't have any kind of work, so this is 0. We are filling a tank, so mass out is 0. So all of this term is 0. Kinetic and the potential energies are not given, then I will neglect also. So it cannot actually reduce to this term. And the M1 initially evacuated, this term is 0. So just we can equate actually M2U2 will equal to M inlet HN. M2 is the same as M inlet. This we can say the final internal energy will equal to the inlet enthalpy. We can calculate the inlet enthalpy from the steam table at pressure inlet condition. Then we can get the final internal energy along with the pressure. We can go to the table to calculate the temperature in this case. But in this case, Shabab, we have unsteady flow for filling a tank with steam. So in this case, I have used the steam tables in this case to calculate the properties. So be careful, because actually some of you, the working fluid is steam, and he just go actually to use PV is equal to RT. This equation, if you have, is for gases. Okay, only applied in case when we have the working fluid is gas. If it is a steam, I will be using the steam table. If it is refrigerant, I will be using the refrigeration table in this case. Okay, so let's look here. Can have another example. He said an industrial, so شباب here, an industrial, not insulated. So when you just read the problem, just read it carefully. Industrial, actually that means nothing for us. This is regarding the application. 8 meter cube rigid tank. Rigid tank, so that means the initial volume will equal to the same as the final volume, which is equal to 8 meter cube. Okay? He said this tank contains air. So the working fluid is air. So I will stick to the ideal gas equation of state. PV is equal to RT, unless he asked me to use the modified equation PV is equal to ZRT. And this is the tank which contains air. He said this air is initially at a condition contains air at pressure B1, which is equal to 600 kilopascal, and temperature T1 is equal to 400 Kelvin. Okay. Look at also the unit of the temperature. In case of gases, usually the table list is a value in Kelvin, but in case of steam or refrigerant, you will find the temperature listed in the table in degrees Celsius. Okay. طيب, he said a valve is connected to this tank, so there is a valve here connected to this tank. Okay. He said this valve actually is open and the air is allowed actually to escape until the pressure actually inside the tank drop down to B2 is equal to 200 kilopascal. So air has left the system to escape, the valve was open and some air has escaped, and the pressure actually based on this drop down to a value of 200 kilopascal. He said actually the temperature during this process has been maintained constant through using an electric heating coil. So electric heating coil is supplying electrical power, okay, to keep the temperature constant in this case. So we have the temperature T1 is same as the temperature T2. We need to determine actually this electric work that actually required to maintain the temperature constant. So we need to calculate the value of the electrical work in this case. Okay. In this case, we have the working fluid is air. So we don't have anything other than actually the ideal gas equation of state. He didn't ask us in this problem to use the modified equation, so I will go ahead with the given equation B1, total volume V1, M1R equal to M1R multiplied by the temperature T1 in this case. Okay. But in this case, we have B1 is equal to 600 kilopascal multiplied by the volume V1, which is 8 meter cube. That should equal to M1, which we need to calculate, multiplied by R for air, which is 0.287 kilojoule per kilogram. This is kilojoule per kilogram Kelvin, and that's why this pressure is calculated in kilopascal. Okay. This gas constant R, if you don't remember, or if it is actually working fluid other than air, we can just get from table A1 depending on the working fluid. This is the R value multiplied by the temperature T1, which is 400 in this case. And based on this, we can calculate actually the mass M1, the initial mass of air, which should equal to 41.81 kilogram in this case. Okay, so this is the initial mass. We want to calculate, our target is to apply the mass equation to calculate the amount of mass that left this system. But we need to calculate first the initial mass, and we have also to calculate the final mass. Then we can apply the mass equation to calculate M exit. And we have at the final state V2, total volume V2 will equal to M2 R multiplied by T2. We have V2 is 200 kilopascal. It is rigid tank, so V1 is the same as V2, equal to 8 meter cube, equal to M2 R, which is 0.287 by T2, which is the same as T1, which is 400 Kelvin. And based on this, we can calculate the final mass M2, which will equal to 13.94 kilogram in this case. Fine. Let's apply the mass equation for a steady flow, which is mass inlet minus mass exit equal to the final mass M2 minus the initial mass M1. In this case, we have actually flow is leaving, but we don't have flow coming into the system. So mass N is equal to 0. So the mass of air that left the system will equal to the difference between the final mass and the initial mass. This is M2, which is equal to actually M2 minus M1. We have here negative sign, so we can take it to the other side. So M exit will equal to M1 minus M2, which is M1 minus M2. M1, we have this value 41.8, M2 is 13.9. If you calculate this difference, it will equal to 27.87 kilogram. And this is actually the mass of air that left actually this tank. Okay. But we need to calculate, our target is to calculate the electric work in this case. So that means we need to apply the energy equation in this case. Okay. But let's apply the energy equation. Now we have mass in. Sorry, we have mass out, M exit, we have M1, initial mass, and we have the final mass M2. Then we can apply the energy equation. We apply the energy equation, will be Q minus work will equal to M exit multiplied by H exit plus V exit plus, let's write it down again, plus GZ exit minus mass inlet multiplied by H inlet plus V inlet square divided by 2 plus GZ inlet plus, don't forget, M2U2 minus M1U1 in this case, okay? Type this term, already we have mass out, but we don't have mass in, so all of this term will be zero. We don't speak about kinetic and potential energy of the leaving flow. If he gives you the velocity of the flow leaving the system and its potential energy, then you can add. But here they are not given, so those two terms will be zero in this case, okay? Type in this case also, he didn't actually give the heat transfer, it is not given or required, so this value will equal to zero in this case. But do we have any kind of work? Yes, we have electrical heating work in this case, okay? Type that should equal to M exit multiplied by H exit plus M2U2 minus M1U1. So we can say actually the work will equal to minus the work input to the system, which is the electrical work, will equal to M exit H exit plus M2U2 minus M1 minus M1U1 in this case, okay? We have all masses, M exit we have calculated, M2 and M1 we have calculated as well. But what about U1, U2 and H exit? This is actually air. U1 we have the temperature T1 is equal to 400 Kelvin. Then we can go to table A17 for air. In this case, this temperature T1, we can get the value of the internal energy U1. Internal energy U1, if we go to the table, will equal to 286.16 kilojoule per kilogram. We set for air or for gases, we'll be using table from A17 to A25 to calculate the internal energy and the enthalpy. And we have also T1 is the same as T2 is the same as T1. So when we go to the table, temperature is the same. So actually the internal energy U1 will be the same as U2 in this case. So we have U1 and we have U2. But what about the enthalpy as the exit section? It's the exit. Actually, the initial temperature was 400, and we have electric heating coil to heat up the air, and the final temperature will be kept constant. That means the outlet temperature here should equal to also what? Should equal to constant, which should equal to the value of 400 Kelvin. But what about if the system actually was at initial temperature, let's say 400, and the temperature has been reduced to, let's say, 300 in this case? So what will be actually the temperature at which I need to calculate the enthalpy at the exit section? In this case, we can say T exit will equal to T1, which is the initial temperature, plus the final temperature divided by 2. In this case, we have T1 is the same as T2, so the average temperature between the initial and final temperature will be the same as 400. But if it is different, I will take the average value of T1 and T2, then I can get the value of average temperature for the flow that is leaving this system. Then we can go to table A17 in this case for air, then we can calculate the enthalpy H exit. Enthalpy H exit will equal to 400.98 kilojoule per kilogram. But this is actually a swapping case of the working fluid is gas. I calculate the average temperature at the outlet to go to the table to calculate the enthalpy. But let's say the working fluid here is a steam. If it is a steam, I need two properties, not only one property. So in this case, he will give you the condition at the exit section will be given for you. We should give you, in this case, in case of steam or refrigerant, to use the table, you should be given, in this case, two properties will be given for you. But in case of gases, we can just consider this assumption, the average temperature at the outlet will equal to the average of the initial and final temperature. Then we can go to the table to calculate H exit. We have the flow is leaving in this case, or also we can do the same if we have flow inlet and we don't have outlet. You can calculate the inlet temperature as equal to actually the average of the initial and the final temperature in case of the working fluid is air. But if it is a steam or refrigerant, the condition at the inlet section or the outlet section will be given for you in this case. We should give you in this case two independent and intensive products. But in this case, we have calculated everything. We have H exit, U1 and U2. We have M exit, M2 and M1. Then we can calculate the electrical work in this case. If you calculate the electric work, it should equal to a value of 3,200 kilojoule. So that should be 3,200 kilojoule in this case. And it should be of negative sign because this work is input to the system in this case. Okay. By this, Shabab, we are done with the whole of chapter 5. Inshallah, next time we'll be starting chapter 6.